So, as it is customary, I'm going to talk about my PhD thesis, since I have finished working on it in between the two conferences. Well, actually, the very beginnings of all of this theme was something I talked about 2 conferences ago, but in a much more basic sense because I was a master's student at that point. So, the main focus here will be, of course, acceleration of cosmic rays. But I will cover 2 a bit different topics. I will talk about acceleration in supernova remnants on smaller scales, but also in accretion shocks at larger scales. Still, no matter where the cosmic rays are accelerated, they interact with the interstellar medium, producing various products like gamma rays, neutrinos, and lithium. Of course, there are many other things, but these are the things that I will be focusing on. So, the basic thing about these hadronic interactions are collisions of cosmic ray protons or alpha particles, or in some cases some heavier particles, with these same particles that have much less energy and that are located in the interstellar medium. So when these 2 particles collide, neutral and charged ions are produced, but these particles decay very quickly. And when neutral ions decay, they produce 2 identical gamma rays that we can observe and find out more about the cosmic rays that produce them. On the other hand, the charged ions again decay, producing various neutrinos again that we can observe and learn more about the cosmic rays that they originated in. Also, there is another very simple interaction where 2 alpha particles, again one from cosmic rays, one from the interstellar medium, collide, producing lithium and other light elements, but we will focus here on lithium. So the whole story actually began with the consideration of Fermi Large Area Telescope observations of the whole sky. So the whole sky looks like this. Of course, it is brightest at our galaxy is the brightest one here, but as you can see, there are other very bright point sources. But when all of this is removed, we still have very much contribution of the gamma rays all over the place. So this actually represents the gamma ray background, which is presented here as a spectrum. And this gamma ray background is not really fully explained. Of course, we know that many unresolved sources, regular ones like star-forming galaxies or AGNs, can contribute to it quite a lot. But still, there is always enough space for some maybe more exotic contributors in order to fully explain this background. So, the thing that we wanted to consider is gas accretion on larger scales. Gas accretion is something that can occur when objects on larger scales are forming. So when we have large virialized objects like filament or on maybe a smaller scales galaxy cluster, accretes additional gas, some kind of shocks can form, and of course, since you have a magnetic field present, you can accelerate some kind of cosmic rays in this type of situation. So we wanted to see how these accretion shocks evolve with time. So actually this is something that has already been done in Pavlidou and Field's paper and in Pavlidou's dissertation. She made analytical models of the evolution of accretion shocks in the universe. She actually presented 3 models, the most simple one being the one where all the accretors are located in the homogeneous medium. So the strength of the shock around each of the objects will depend only because of some objects that are smaller or larger. The second model also includes the variations of the distribution of the environment around the accretors, and the third model is just a bit more complex model too, but with some additional filamentary effects. This is actually the most important graph that we use. It presents integrated mass current from these 3 models, the lowest curve being from model 1, the simplest one, then we have model 2 and model 3. What this actually represents is the amount of mass that passes through all cosmic accretion shocks at each of the redshifts. So we include at each redshift all of the accretors having all kinds of masses and performing all kinds of shocks, so with different Mach numbers. And this is actually what we use to describe the evolution of accretion shocks. We implemented that into our model. We just, well, I'm not going to go into much detail about this, but this is the final equation that we derived. So the cosmic accretion rate is the one that was presented here. So this is this part here, and we just multiply that with the shape of our gamma ray spectrum. Why gamma ray spectrum? It's because, as I already said, these cosmic rays, as any other, interact with the interstellar medium, producing gamma rays. So if you observe gamma rays, their evolution is actually, the cause of the evolution is the evolution of the accretion shocks. So we want to see how much gamma rays can accretion shocks produce, and we multiply the evolution of accretion shocks by, of course, the shape of the gamma ray spectrum. The shape of the gamma ray spectrum in this case is fairly simple. It looks like this. Here there are a few cases presented with different spectral indices, and the spectral index of the gamma ray spectra actually is the same spectral index as the source cosmic rays that produce them. And we have the break of the spectrum at the half pi mass, since, as I said, when neutral pi decays, it produces two gamma rays of the same energy. So we have the shape of the spectrum, we have the evolution, but we don't know how to calibrate our model. So we need to choose some kind of a typical object that we can calibrate our models to. So since, as I already mentioned, galaxy clusters are some kind of typical object for this kind of process, we needed to choose gamma ray flux of observed gamma ray flux of some of the clusters. But unfortunately, at that point, we have the Fermi collaboration couldn't detect any of the galaxy clusters. They only gave us upper limits. So since this was the only thing that we could use, we used flux upper limits, making, of course, our models again upper limits of their total gamma ray intensity. So we chose to use coma cluster, and when we implemented that into our model, we got these curves. You see three plots here because the first one, the lowest one, is when we use the first simplest model of the accretion shocks, then the second one, and the third one that is the most complex, but also the highest one. Obviously, especially this most realistic model overshoots the Fermi gamma ray background presented with these data points. But of course, you have to have in mind that these are still upper limits because we normalize to the upper limits. So the real flux of the coma must be much lower than this, and when we normalize with the real flux, all of this will be lower. Spectral index is a free parameter, so that's why I plotted here our models for various spectral indices from the strongest one, 2.0, to the 3.0 and much weaker shocks. But still, even in this case, you see that maybe the simplest model for some of the weaker types of shocks can even be consistent with the data. Later on, I think the following year or 2 years later than that, after that, Fermi collaboration actually published another paper with more recent upper limits for the coma cluster, which were 3 times lower than the previous one we used. So I just plotted the same type of a plot here. So the dashed curves represented the old curves, and the new ones are done with the new upper limit. So as you can see, in case of, for example, 2.7 spectral index, now our curves used by done with model 1 and model 2 actually are consistent with the Fermi gamma ray background. Only the third one overshoots the data, but still, again, keep in mind that this is still an upper limit, so our curves will definitely go even lower in the end. But at this point, we thought about maybe finding another way to better constrain our models. So we wanted to use neutrinos, because neutrinos, again, as I said, are easily produced by cosmic ray interactions. So, of course, the best neutrino detector is IceCube, and the IceCube collaboration released a paper where they reported a few dozens of applied detected events, neutrino events, which were not correlated to any galactic source or to any point source on the sky that they can resolve. So, but somewhat we can think about all of these sources as some kind of neutrino background that was similar to the gamma ray background we used before. So if we think about it that way, we can use it to constrain our models. The link between gamma rays from any source and neutrino is very simple. And for example, in case of strong shocks, where the spectral index is 2, the actual gamma ray spectrum will be just 2 times larger than the neutrino spectrum of that source. Of course, only if we consider just one type of neutrinos. At that time we had only 37 neutrino detections, and there were 2 papers where they gave us the best fit of those events. So I used both of these fits, and I consider them as some kind of neutrino background for our fitting. So when we normalize to neutrinos, we get something like this. So these gray boxes here represent ice cube background, the old one and the new one. So when we translate this neutrino background to the gamma rays using that same simple connection, for example, in this case, the gamma rays, this is spectral index 2.0, gamma rays are just 2 times larger than neutrinos. So we translate neutrino to gamma rays and then normalize our curve not to overshoot these gamma rays. So our curve from our modeling here for spectral index 2.0 is this black curve. The red curve here is the same curve, but including the losses of some gamma rays that always occur at highest energies because of the interactions with the extragalactic background light. This happens to any gamma ray source. So the red curve is the main one. I also plot on all of these plots this dotted curve here, which represents contribution of normal star-forming galaxies that are unresolved, and this dotted line, that just a straight line, these are quasars. The black curve here represents the summary of these 3 contributors. The black data points are Fermi gamma ray background, the new data points at this point that were released. So I also plot all of these curves in case of spectral index 2.3 and 2.6, just to show you how all of this is different. So as you can see, if most of our accretion shocks are strong, like in this case, neutrino background is much more constraining because it doesn't let you go very high. And in this case, if this was the case, then we still have a lot of space here at the lower energies for other contributors like star-forming galaxies. And when we summarize all of this, we do not overshoot neither gamma ray background nor neutrino background. So this could be a potentially consistent picture. For spectral index 2.3, this is like some limiting case where we still are okay with both of the observations. But in case, for example, of the more weaker shocks, we cannot use neutrinos to normalize our model, because then we will shoot for a lot the gamma ray background. So the gamma ray background in this case would be much more constraining. In this table here, I just present that in case we want to use neutrinos to normalize our accretion shock models, we can, for example, in case of strong shocks, explain, if we don't use attenuation, which is not realistic, we can explain 29 to 46% of the gamma ray background. But if, of course, we implement the EBL attenuation, we can only explain 12 to 18% of the gamma ray background, which, in my opinion, is much more realistic. But still, you see that these type of shocks can actually make an important contribution and have to be considered. So with this, I will go to the, well, a bit different topic, but still the same. It's something that, again, appears from interactions of cosmic rays that I have also done. It's the production of lithium, and lithium is extremely interesting and important because it's one of the elements produced in the Big Bang nuclear synthesis, as well as deuterium and helium, but it is the only one that where BBN abundances do not match the observations. So many people work on understanding lithium and its abundances in various environments. Why we chose to work with lithium is because there are many observations of lithium in the Milky Way, but just a few years ago, first published observations outside of the Milky Way were made, and these are in the SMC. And what is interesting, the SMC abundances are fairly close to the BBN abundances, contrary to the Milky Way abundances, which are much lower. And this is the thing that is actually strange. They shouldn't be this low. But on the other side, you don't see such a thing in SMC. So we wanted to understand and see how much of this SMC lithium abundance could actually be produced by interactions of cosmic rays produced in its supernova remnants with interstellar medium, to see that is this maybe the reason for a large lithium abundance. So the lithium can be produced through fusion reactions of two alpha particles, again one from cosmic rays, the other from the interstellar medium, or from spallation of heavier elements, CN and O, when they collide with the protons or alpha particles. So we included both of these reactions. The link, again, since they are both produced, gamma rays and lithium are produced from cosmic interactions, the link between them is easy, and we wanted to link this with gamma rays because we also have the observation of gamma ray flux of the SMC, so maybe the link will tell us more about this problem. Of course, the thing that you have to keep in mind is that lithium is something that accumulates over time. So the observation of lithium is lithium produced through its whole history, while its gamma ray flux is something that is present. So we needed to just use this present gamma ray flux to model its whole gamma ray history in order to be able to compare it with its lithium. So we did something fairly similar as previously with accretion shocks. I know it's the formula is large, but it is actually pretty much more or less the same as the one for the accretion shocks. The only difference is this is now not cosmic accretion rate, but cosmic star formation rate. We for this we used the model cosmic star formation rate derived by illustrative simulation, because it's a very nice simulation that can give us cosmic star formation rate in various mass bands, so for galaxies of different masses. So we used the one closest to the mass of SMC, used it here, and again everything else is more or less the same. So the resulting curve would be here. So these are all small unresolved galaxies similar to the SMC. I also plot here the unresolved galaxies similar to the Milky Way, so you can compare the two curves. This is again Fermi gamma ray background. As you can see, what is also expected is these galaxies are have a much smaller contribution, actually less than 1%, while the Milky Way-like galaxies have around 50% contribution. The interesting thing is that when you use this curve and combine it with lithium, you can only explain less than 1% of the lithium observed in this galaxy, which was really strange, because then it raises the question, why do we have so much lithium if we cannot produce any of it, more or less any of it, with cosmic rays. So we even did an extreme test, like let's imagine that whole this background is actually produced by small unresolved galaxies. Of course, this is not realistic, but let's imagine that. And then use this in our equation with lithium and derive the lithium. And we can, if we use that, which is very extreme, we still can can explain only 55% of the observed lithium-6 and 12% of the lithium-7. So even in this unrealistic case, we still cannot explain by galactic cosmic rays this lithium. Of course, this raises a lot of questions. It makes us think that maybe some other cosmic ray populations are important here, like those that can be accelerated in tidal cosmic rays in the interactions with the Milky Way. So on smaller scales, as I said, we see that still, even in such a simple case, we still have to think about some more exotic types of cosmic rays, not just galactic cosmic rays. And also, as I said before, on larger scales, we also investigated a more exotic type of cosmic rays accelerated in accretion shocks. That's all. Thank you.
People have mentioned accretion shocks for making ultra-high energy cosmic rays. Do you get a limit on whether that is reasonable from?
Well, I guess why not? I mean, when we did our models, I didn't see most of the shocks were not extremely strong, but on the other hand, they live much longer, they are larger, so I think that you have much more time to accelerate these particles, so why not? I hope so. It would be interesting.
Any other question? If not, then we thank our speaker and all our speakers this morning.